So essentially over the next 45 minutes, both Kristin and I will give you some overview over what we do in the Institute of Geophysics and Extraterrestrial Physics in our university, which is much smaller than UNAM, but and very technologically kind of focused. So engineering and also physics are kind of like the focus points of the university. Okay, so first of all, this is the Institute of Geophysics and Extraterrestrial Physics. You see a group photo here. Not every person is actually represented on that, but it's actually a relatively big institute of the Faculty of Electrical Engineering, Information Technology, and Physics at TU Braunschweig. And in total, there are 5 groups at this institute, and the 5 groups do slightly or actually quite different things. So we have from top to bottom solar system astronomy with Professor Jessica Agarwal, then planet formation and small bodies, urban geophysics, applied geophysics, and then in the last, space physics and space instrumentation, which is our group, and I will introduce a little bit more what we do in our group. Just for your reference, what the other groups do, so especially applied geophysics and urban geophysics, they investigate, for example, permafrost soils from northern Scandinavia, for example, but also the water content, subsurface water content in urban environments, like why trees, for example, grow in one place in the city and don't grow in another place in the city, and things like this. Then solar system astronomy, this is about remote observations, especially of comets, their coma, how they develop when they go close to the sun, for example, what the composition is. So this group has been heavily involved also in the Rosetta mission, also the European Space Agency, to comet 67P, Churyumov-Gerasimenko. And then the group of Jürgen Blum, planet formation and small bodies, they try to investigate planet formation in the laboratory. So essentially how small particles like dust particles stick together or how they fragment, also under zero-G conditions. So they have like drop tower experiments where they see how this kind of like sticking together and planet formation in its infancy works when like a molecular cloud collapses. And as I said, space physics and space instrumentation, this is our group. And so for the rest of the talk, I will introduce a little bit of our activities. So most of our activities are centered about the interaction of the solar wind with Earth's magnetic field or any other magnetic field or atmosphere of a planetary body. So what happens? The solar wind is a constant stream of particles, mostly protons and electrons, that streams off or flows off radially from the sun continuously. There are variations, but it's continuously present. And these charged particles, they cannot enter, for example, Earth's magnetic field very easily, not directly. And that means that some interaction region has to form so that the solar wind can flow around this obstacle that the planetary magnetic field poses to the solar wind. And so a structure like this will emerge, which is Earth's magnetosphere. So we see here in gray the region where the magnetic field of Earth will be dominant. So this is the actual magnetosphere. And this magnetosphere is compressed on the day side, which is closer to the sun, and then expanded on the night side, which is the magnetic tail of the Earth in this case. Then we will have a region, this is the magnetopause, like a thin sheet separating the magnetosphere from this previous part where we see the solar wind coming in. The solar wind is coming in here from the left. And since the solar wind is super magnetosonic, that we say, or supersonic in the frame of reference of the Earth, the information that there is an obstacle ahead of the solar wind cannot directly run or penetrate into the incoming solar wind. And that means that in this configuration, a bow shock has to form here in front of the magnetosphere. And at this bow shock, the solar wind will be decelerated, thermalized, compressed, and then kind of like put into a state that it then can flow around the actual magnetosphere within this intermediate region, which we call magnetosheath. And then significant part of our activities is centered around the foreshock. So the foreshock is this region here. And this is actually the region that is magnetically connected to the bow shock. So the solar wind carries its own magnetic field, or the solar magnetic field actually, which is called interplanetary magnetic field, towards the Earth. And we have in this foreshock region, which is magnetically connected to the bow shock, we have some of the particles that are being reflected at the bow shock and then kind of like interact with the incoming solar wind. And this gives rise to quite a few phenomena. For example, to extended wave fields, as you can see here in the simulation. Like from a hybrid simulation, you can see here like this extended wave field. And the wave field is created in the foreshock, but of course, the solar wind is supersonic. It is kind of convected back also to the bow shock and interacts then with the bow shock. And that means that the bow shock itself will look very different here, we call quasi-parallel bow shock, with respect to down here, which we call quasi-perpendicular bow shock. Yeah, the quasi-parallel bow shock is downstream of the foreshock region. And since we have this very extended wave field there in the foreshock region, this quasi-parallel bow shock also is not like a thin sheet, but it's more like a patchwork of different structures of the wave field that then form and reform continuously this bow shock. And that also means that the magnetosheath region that we have behind will be very turbulent and also very, full of or rich of many different structures within the sheath region. And one of the structures that we are investigating are jets. So these are essentially localized structures where the dynamic pressure is enhanced with respect to the surrounding environment in the magnetosheath. So you can think of it like something like this. Usually the plasma goes through the bow shock, it is decelerated, it is deviated, so the direction changes, and then it flows around the magnetosphere and the magnetopause in the magnetosheath. But within the jets, the plasma has a direction that more resembles the direction of the solar wind, and the dynamic pressure is very much enhanced. So density and velocity. And you can see this, for example, in one example plot over here. So in the upper panel, we have the velocity, and x usually in the magnetosphere points towards the sun. So the x component is here in blue, and you see that the velocity in the x component goes up, actually in minus x, because we are looking for the solar wind coming from the sun, so it goes against x. And then at the same time, we see here the dynamic pressure at the position of the spacecraft going up dramatically. So this is the dynamic pressure in the solar wind. This is 1/4 of the dynamic pressure of the solar wind, and usually in the magnetosheath, we are even below that, and you see that this in the sheath region goes dramatically up, and this is a jet, okay, in the magnetosheath. And these jets are actually quite interesting for us for multiple reasons. And the reason is just that, first of all, they are conceptually interesting because they connect the upstream foreshock region, upstream of the bow shock, with the magnetopause and with the magnetosheath, usually the magnetosphere. Usually the magnetosheath is like a very turbulent region, and structures that are created upstream are kind of lost in this kind of like sea of turbulence. Yeah? But with the jets, we have like a coherent structure that kind of like can bridge this gap between the bow shock and the magnetopause. And so like temporal scales and also spatial scales can then be transmitted from the foreshock region to the magnetopause and then into the magnetosphere. And then in the magnetosphere, we have also quite different phenomena that can result from the interaction of the jet with the magnetopause. First of all, we can create magnetopause surface waves, actually very high amplitude waves, about approximately 1 RE deep, for example. What is an RE? An Earth radius. The Earth has a radius of approximately 6,370 kilometers, and the magnetopause, so the distance here from the Earth to the magnetopause, is typically 10 Earth radii. Yeah? And usually we have like maybe variations of a couple of 100 kilometers or so of the magnetopause. Now, if a jet hits the magnetopause, it can go in very easily several thousand kilometers. Okay? And for example, launch surface waves on the magnetopause that are also visible and transmitted inward into the magnetosphere. For example, be seen here at the geostationary orbit, or geostationary position. Another thing that can happen is that these jets can cause magnetic reconnection at the magnetopause. And magnetic reconnection is essentially the main driver of magnetospheric activity and also space weather inside the magnetosphere. So these jets also are geoeffective in this sense. So they can cause effects that we would associate with geomagnetic activity and with space weather. And then there are other things that can happen. So they have been observed, for example, in ionospheric flow enhancements. So you can observe them from the ground, looking into the ionosphere with radar data, for example, or in terms of like dayside auroral features. They have also been observed that, like in the winter, you have like an imager somewhere in the up north at night, well, locally at night, but still looking out to the dayside magnetically, you can observe these features. And also you can see them in ground magnetograms also here in this region. And the interesting thing about this jets is also that this don't happen like once every couple of months. But yeah, on average, really large-scale jets impact the magnetopause once every 20 minutes. And that is on not so good conditions. So in like favorable conditions, this can occur every couple of minutes, essentially. And just the large-scale jets, like smaller-scale jets, will come there much more often than that. So this is one of the things that we investigate using in situ data from satellites from different ESA and also NASA missions, like Cluster and Themis and MMS, for example, so different Cluster and ESA multi-spacecraft missions. But we do not only use the data, we actually also contribute to generating this data by developing and manufacturing spacecraft instrumentation. So especially magnetometers, but also magnetometry booms. So this is a different activity that is also performed in our group. So we have contributed the magnetometers, for example, here to the Themis spacecraft. And so you see now a completely different picture. We use the data from the spacecraft, but we also do some hardware, for example, flux gate magnetometers with very low drift and also in large temperature ranges, which is maybe not so important around Earth, but it's very important if you go to other planets, like to Jupiter, where you are kind of like on the cold end, and then Mercury, where you are on the hot end, kind of on the spectrum, very close to the sun. And then the digital electronics, they are manufactured from a company in Germany, so we don't do this ourselves. And with some colleagues in Belgium and in Sweden, we also construct, first of all, these booms, but then also like integrate our own sensors, for example, in these Langmuir probes. So this is like what you see here is one of the qualification models for the Comet Interceptor mission from ESA, where like our sensor is inside of this Langmuir probe, and then there's a second sensor closer to the hinge here to kind of like have dual sensor measurements to then later be able to extract or correct for spacecraft noise or spacecraft interferences in the data that we measure with these sensors. And in this respect, we have quite a bit of expertise in all of these kind of like surrounding areas. So this goes from magnetic field cleaning activities, so identification of all of these disturbances that come from the spacecraft, calibration both on ground and in space. For the calibration on ground, we have this calibration facility that is literally in the woods near Braunschweig, because you need like a magnetically clean environment. So just to give you an impression, so when somebody comes with a car and parks like 100 meters away, you can discard the measurement. Yeah, so because you are kind of like making a lot of magnetic noise, and this has to be accounted for. So yeah, literally in the woods. But we also do some thermal design, for example, which is necessary to put like magnetometers or instruments, for example, on planetary missions, and then also do or contribute to magnetic cleanliness activities at ESA and at NASA, which benefit then, of course, our own data, but are necessary in this context. Okay, so our magnetometers, I mean, this goes back for several decades in history, much more than I have been at the Institute. So have been just a professor for about 3 years at the Institute. But then in the past, these magnetometers have also flown or are still flying on different missions. So the heritage comprises these missions and more. So Venus Express, for example, which is long gone, mission of ESA to Venus. Themis Artemis, this is still a current NASA mission. We've also built the Rosetta magnetometers, both on the spacecraft and on the lander Philae, on the Hayabusa 2 lander, Mascot. And our magnetometers are, for example, on board Bepi Colombo. on the spacecraft en route to Mercury. So this is the Mercury part of the talk. And they're also on the JUICE spacecraft en route to Jupiter. So this is both ESA missions going to both kind of like extremes of the solar system. So you can see here on this side. And so for the next couple of minutes, I will actually talk a little bit about the JUICE mission. So you see the JUICE spacecraft up here. I can also show you where the magnetometer is. So our magnetometer is here. This dot, 1 pixel probably on this picture. And the JUICE spacecraft is supposed to go to the Jupiter system. So we see Jupiter in the background, and then visit these very interesting moons that you see here. Because Jupiter, a little bit unlike Earth, is kind of a planetary system in its own. You know? So again, we now go to Jupiter, and I will tell you a little bit, few informations about the Jupiter system. So Jupiter has in total 80 moons, maybe by now a few more. But of those, there are 4 main moons, and these are called the Galilean moons. Okay, the Galilean moons are Io, Europa, Ganymede, and Callisto. And many of the other moons are just a few kilometers actually in diameter. So they are very small rocks that orbit Jupiter, but are also, well, in the list of moons of Jupiter. Why are they called Galilean moons? Because Galileo Galilei actually found these moons as a first person, with a back then a very novel instrument which was called the telescope. So this was the innovation of the day. And back then also, by the way, there were actually disputes with another person whose name right now I don't remember, but they were both claiming, oh, I've seen it first. But in the end, like also comparing different calendars that were being used, by now we know that Galileo was first by a few days. Anyway, so it's rightly attributed, called Galilean. But apart from this, you have also, of course, many different other moons and a small ring system that is not so prominent as with Saturn. Now here you see the Galilean moons in comparison, and they are very different, by the way. So we have Io. Io is very close to Jupiter, and so has just like an orbital period of 1.7 days. So it's very close to the central body. And due to the tides, is very volcanically active. So it gets like internal heat by the strong tides. So this is the most volcanically active body in the solar system, and spits out a lot of like sulfur dioxide, for example, and sulfur that is then kind of like expanded or distributed inside of the Jupiter planetary system and also Jupiter's magnetosphere, especially. And within all of these moons are within Jupiter's huge magnetosphere. We have Europa, Ganymede, and Callisto, and these are called also the icy moons. And why icy moons? Because they contain a lot of water, especially these 2 outer ones. And you can see this because the density is significantly lower than of usually rocky moons, also in comparison, for example, to our own moon. Only Europa looks like very icy, so that's because there's probably some cryovolcanism going on and kind of like reforming and refreshing the surface. Then Ganymede is special because it's the only moon that we know of that has an internal dynamo going on, so it has its own intrinsic magnetic field that interacts very significantly with the magnetic field of Jupiter. And then we have Callisto, and Callisto is interesting because it has a very old surface. So it's not very, I mean, the internal part is not very differentiated probably. So they're not like layers or so. And the surface, it's not active. So the surface is very old. And what happens when the surface is very old in the solar system? Well, periodically you will have like meteoroids or asteroids, you know, hitting the surface and making a crater. And if you have like a volcanically active surface, then or body, then that means that over time, this will be renewed. The surface will be renewed. But if that doesn't happen, then you keep accumulating craters essentially, and that is what's happening on Callisto. So it's completely full of craters, and some of them are actually very large. So this is like one crater here, by the way. Okay, and Jupiter, or JUICE, is called Jupiter Icy Moons Explorer. So it will visit these 3 outer icy moons of Jupiter, make flybys around them, and then at the end of the mission, go around an orbit, stable orbit around Ganymede to especially study also its magnetic field and its environment and also the interior. Okay. So what is the main objective of the JUICE mission? The main objective of the JUICE mission is actually not to learn specifically something about the magnetosphere, but to learn something about habitable worlds around giant planets. That's essentially the main objective. And why? Well, we know that in our solar system, there's one place that there is life, and we happen to be on it. But then, of course, if there were a second place where there would be life, on Mars maybe, or here, then that would increase, of course, dramatically the chances that everywhere in the universe there are also maybe other planets or other moons that there would be life. And well, life on Earth is based also, especially on the liquid ocean or the presence of liquid water. And but the moons, Jupiter, are far out in the solar system, so there could not be any liquid water on the surface. It will all be frozen. However, where can we find these liquid water oceans? In the subsurface. So there's evidence that below the surface of the moons there might be actually a surface, an ocean of liquid water, and if there are other conditions that are necessary for life, then there might be the possibility that actually life is developing inside of these oceans. And which are these other conditions? Well, the other conditions are you need energy. In our planet, that's the sun. Okay, that doesn't work inside the moons. But here, or radioactive decay, you can also have in heating the internally the Earth. But especially the tides are very strong sources of energy for the Jovian moons. You need essential elements. So the JUICE mission will also be equipped with spectrometers, for example, to sample or to see the composition of the surfaces and also maybe of some vents if they exist, for example, on Europa, see what is inside actually of the moons. And then, of course, you need also stability of the conditions on geological timescales. Okay. Then, of course, we are contributing one of the magnetometers to an entire system of magnetometers to this JUICE mission. And the question would be, well, in the context of habitability or of determining the characteristics of the subsurface oceans, what can the magnetometer contribute, right? And well, that's actually the magnetometers of the Galileo missions were the ones that kind of provided the evidence that there might be a subsurface ocean. And how can that be? Well, Jupiter has its own huge magnetosphere, huge magnetic field, huge magnetosphere. And the Jovian moons, these Galilean moons, they are running around Jupiter, orbiting Jupiter inside of this magnetosphere. So we have very predictable changes in the magnetic field at the positions of the moons along their orbit around Jupiter, okay? And these variations in the magnetic field, if we have like a conducting interior, they will generate currents inside, and these currents will generate secondary magnetic field. And if we are close to the moons and we know what the sources is in terms of primary magnetic field, then we can disentangle the secondary magnetic fields from the induced magnetic fields. Yeah, maybe also from some crustal magnetic fields if we have like several flybys. And that is essentially the idea to then by modeling to determine if there is like a highly conducting subsurface ocean in comparison to just rock, for example, which would have a completely different signatures along the orbit of the JUICE mission. And this way we can actually characterize, for example, also the interior of the moons using magnetic field data. And here what you can see is also on the magnetosphere. This is of course just a drawing. If the magnetosphere of Jupiter would be visible, then it would be huge. It would be by far the largest object on the night sky that we would be able to see from our position. Okay. So this is just to see how the magnetometers look like that are flying actually on JUICE. So we have contributed this. This is our inboard sensor. Then there is an outboard sensor which comes from Imperial College. So the PI is Michelle Dougherty from Imperial College in London. And then there's a third sensor. This is actually a scalar magnetometer coming from the Institute or Space Research Institute in Graz. So there are 3 European institutions involved in this instrument. And then at the top left, you see the electronics box to which all of the institutes have contributed their their actual cards. And this is actually the last slide that I have on Jupyter, just that you see the timeline. So I would almost say also space missions work on geological timescales. Yeah, so nothing for PhD 3-year projects, unfortunately. So the planning started like 10, 12 years ago with a proposal. Then was a lot of developing, working on the hardware, manufacturing, and so on. And the start was actually in April of last year. This was the launch on board of one of the last Ariane 5 European launchers. And then we already had in August of this year a first flyby. It was actually the first also lunar Earth flyby. So kind of like first a flyby on the terrestrial moon with a small course correction, and then a flyby around the Earth to bring it on a course to Venus. So there will be in August next year, there will be a flyby at Venus, and then a couple more flybys at Earth. And the arrival of Jupiter will be in July 2031. Okay, so this is when we will start beginning with the main phase measurement. So we have to be a little bit patient for Jupiter data. And then things will develop pretty quickly. So we will have 35 encounters, flybys at the icy moons, and then an arrival at Ganymede in December 2034, and then go into stable orbits around that moon, and yeah, make more measurements around that moon that has its own magnetic field and how it interacts with the Jovian magnetic. And so now we have gone out to the solar system, and we will go into the solar system next. So this is just a transition slide so that you see just the scale difference. Yeah. So we are at Jupiter here. This is the Jupiter magnetosphere, and just the inner part, yeah, is as big as Saturn's entire magnetosphere. And the Earth's magnetosphere actually fits completely into Saturn's planet. Yeah? And Mercury's magnetosphere completely fits Earth. Just that you see what the scale differences are of these phenomena in our solar system. And with Bepi Colombo, we also have a spacecraft going to Mercury. And so I give the presenter and the microphone to Kristin.
Yes, hello everyone. My name is Kristin, and thank you for the introduction. I'm a PhD student and I work on Mercury. So now, as Ferdinand already said, I'm going to take you to the inner solar system. But first of all, who is Mercury? One of them is Moon and the other one is Mercury. Can you guess? Can you just point on it? Which one is Mercury? Yeah. It's surprising. You're all right. That one's Mercury and that one is the Moon. So here's a little overview about the planets in the inner solar system. So here on the left, you've got the Sun, and here you see Mercury, our innermost planet, then Venus, we are on Earth, and there you can see Earth, Moon. There you see Earth, Moon, and they look quite similar. And Mercury is not much larger than our Moon, and you've got Mars there on the outside. So Mercury is a planet of extremes. So it's the innermost one, it's the smallest one, and it's the one with the most elliptical orbit. And Mercury is going around the Sun in 88 days. So one Mercury year is 88 Earth days, and one Mercury day is 56 Earth days. So there's a 2 to 3 resonance. And the person who discovered that is called Bepi Colombo, Giuseppe Colombo, and that's where the mission, where the mission got its name from. I don't know, did I do that? Well, I just go on. So, and Mercury does not have an atmosphere. So the magnetosphere is not connected with any ionosphere or atmosphere. So that's different compared to Earth. And the slide which I have shown you before, we can all see that from Earth observations. But we know more about Mercury. There have been several space missions going to Mercury. And the first one was in the 1970s from the NASA, and it performed 3 flybys at Mercury. And before, people thought, okay, Mercury is just rock in space. But then a very smart guy said, no, you should put a magnetometer on board. And they did, and they found out Mercury has an internal magnetic field. So there's a dynamo inside Mercury producing this magnetic field. And so Mercury here does have a magnetosphere, and no one expected that before. So NASA went there again. The second time, they built a spacecraft which went into an orbit around Mercury. And this spacecraft was in orbit around Mercury for 4 Earth years, from 2011 until 2015. And we use the measurements of that mission for preparation for our next ESA mission, which is Bepi-Colombo. And that is already on its way to Mercury. It was launched in 2018 and will arrive at Mercury at the end of 2026. And Bepi-Colombo has 2 orbiters, so we will have a multi-point measurement around Mercury. But first of all, I want to go into a little bit more detailed information about the magnetic field. At Earth, it's roughly like this. So you can imagine there's a magnet inside Earth, and the same happens at Mercury. You've got this dipolar magnetic field. But what is special about Mercury is that it is like this. It's offset towards north. So when you measure the magnetic field at the north pole of Mercury, it's way stronger than at the south pole. And we're still not sure why this is the case. So dynamo people are simulating this. We know that there's this large offset. Here's a picture of of Mercury and the magnetopause. Here you can see the magnetopause, and here there's the planetary equator, and there's the magnetic equator, and this has an offset about 20% of the planet's radius. So here I wrote RM. This is Mercury, the radius of Mercury. So as Ferdinand already explained, at Earth they calculate with Earth radii, and here I calculate with Mercury radii, which is roughly 2,400 kilometers. And this is offset about like 500 kilometers. And so I already told you we've got this northward offset. And what is also very interesting is that Mercury has a very axis-symmetric magnetic field. When you look at other planets, there are some anomalies like at Earth, but Mercury's field is very axis-symmetric and it is very weak. When you take Earth magnetic field and the size of Earth and just scale it down to the size of Mercury, you would expect a way stronger magnetic field. So this is very weak, and Mercury is very close to the sun, so we've got a strong solar wind. So we have a very dynamic interaction between the solar wind and Mercury. This produces a very small magnetosphere compared to Earth and very fast and dynamic processes. Maybe you've heard of the Dungy cycle. So this is the time of I don't know how to say that, reconforming the magnetosphere. So at Earth, that is like 1 hour, and at Mercury, it is between 1 to 3 minutes. So everything is very fast there. So now I already told you a lot about a lot of the details about Mercury's magnetosphere. So why should we go there again? Don't we know everything? Here are some science objectives of Bepi-Colombo. There are many more instruments on Bepi-Colombo, but I can't go into detail about all of these. So there are cameras, plasma instruments, laser altimeters, and there are lots of open questions. So the science objectives of these missions, and our magnetometer will contribute mainly to these 2 ones. So we want to investigate the characteristics and the origin of the internal magnetic field. And we want to investigate the structure and the dynamic of Mercury's magnetosphere. Here's a sketch of the spacecraft. So here you can see the 2 orbiters. This one will be a bit further outside. This is the Japanese contribution. There's the shielding, and this is the orbiter which will be closer to the planet. This is called MPO, and here's the transfer module. And at the moment, they are stuck together. They're going to Mercury, and when they arrive at Mercury, they will separate there. The launch was in 2018. We performed several flybys. Now, in September, we had the 4th flyby, and in December, there will be the 5th flyby. And we will go into orbit in November 2026. So we will have the results of that before we can work on JUICE. Here you can see Bepi Colombo as it was still on Earth. So here is the Japanese spacecraft, and here you see the yellow arrows, and here are our spacecrafts. And when they are in space, then then they are on a boom and they are further away from the spacecraft. Here you can see a sketch of MESSENGER's orbit, so the spatial coverage. We will concentrate on this one first. So X is pointing towards the sun. So here's the sun. So here you can see day side, night side, and Z is towards the north. So North Pole, South Pole. And the black lines show the orbit of MESSENGER. So MESSENGER was in an orbit, so always very close to the North Pole, and then very far away at the South Pole. So we only have measurements close to the surface above the North Pole, and no one's ever been at the South Pole. And I drew the magnetopause and the bow shock for you. So we only have measurements in this area, but no one's ever been up here or below the South Pole. And MESSENGER's orbit just performed crossings like here and there, and our spatial coverage is, well, not so good so far. And Bepi Colombo will have an orbit like this. So MPO will be very close to the planet, and the other one is MMO, which MMO stands for magnetospheric. So the M is Mercury magnetospheric orbiter. So this will be in the magnetosphere, and this one will be close to the planet. So we've got a multi-point measurement, and we will cover most of these regions. So this will be very interesting to analyze. Yes, and with that, I want to close, and we want to thank our entire working group, and thank you very much for your attention.
And for a few questions, so if the audience first and then the social media. ¿Alguno que quiera preguntar algo? Very interesting talk. Thanks. Something here? Okay.
Thank you very much. It was really entertainment, really clear in some topics. I have a little question, maybe about in which condition.
Okay, so the jets happen usually downstream of the quasi-parallel shock. Maybe actually I can go, yeah, maybe I can go back to the very quickly. Sorry. Okay, so the jets, we find them usually downstream of the quasi-parallel shock. That means of the shock that is kind of patchy and very, yeah, let's say corrugated or undulated or so due to the incoming waves from the foreshock. So it's downstream of the foreshock region. And when we observe jets, for example, here in the subsolar region, then we can associate this with low cone angle conditions of the interplanetary magnetic field. So of low cone angle, that means if the cone angle is low, we'll have kind of radial interplanetary magnetic field. the foreshock will be located in this region, and then just downstream of this, we will observe the jets. Jets are also connected to higher velocities of the solar wind and lower magnetic the IMF.
Thanks. It's modulated with the sun's activity?
With a solar, you mean like solar cycle, for example?
Yes.
Yeah. Yes and no. So if you just take the measurements of the spacecraft, for example, orbiting Earth and taking measurements in the magnetosheath, and compare, for example, the input data from the Lagrange point 1, that's the solar wind data, then you would see actually a difference in the solar cycle. But then Laura Vuorinen from University of Turku in Finland did a study and showed actually that this is just due to differences in the upstream parameters and the conditions of the solar wind. So if you correct for this, then you see no difference. So it is, you see a solar cycle difference, but it is based on just different solar wind conditions.
Otra pregunta, te lo paso.
Thanks, very interesting talk. Are within the Jovian magnetic field, yeah. So there must be some very interesting interactions between Ganymede's magnetic field and Jupiter's magnetic field. So maybe you said this and I didn't understand, but is JUICE meant to study these interactions, or is it meant to study just Ganymede's field?
No, it's meant to study these interactions. And you're right. I mean, I don't have a slide for this, but maybe I can just say it very briefly. So Ganymede has its own internal dynamo and kind of a dipole field, let's say, and it's going around within Jupiter's magnetosphere. Interestingly, in that respect, also it will face like an interaction with the solar wind without the solar wind. So in Jupiter's magnetosphere, Io is providing the plasma. So Io is very volcanically active. It's like spitting out tons of not tons, but maybe in sufficient mass to then, due to photoionization and electron impact ionization, produce a plasma. And this plasma is accelerated within Jupiter's magnetosphere due to the very fast rotation of Jupiter itself. So although Jupiter is very massive, it rotates around itself once every 10 hours. Okay, so this plasma from Io is accelerated, and then due to charge exchange processes, for example, it becomes neutral again, it is ionized again, and that kind of like expands the plasma all around a disk, essentially, where all the moons lie in kind of like the ecliptic for Jupiter, and so also reach Ganymede. So you will have plasma coming in, which is from Io, but it's coming in around at Ganymede, and then this plasma, or the conditions, are just borderline super magnetosonic or supersonic, which means it will be very interesting to see exactly this shift between, oh, they are super magnetosonic, we will see a bow shock around Ganymede, or they are not, and then what we will actually see is what is called Alfvén wings. So kind of like stretched out Jupiter field lines going through Ganymede, reconnecting with Ganymede's magnetic field, and then going back. And you can actually see this also for the other moons, especially for Io, actually as this interaction due to these dots. Like, oops. Here we go. So this one, for example, this is Io, connected by magnetic field lines, and the interaction with these Alfvén wings means there's like some obliquity to the magnetic field, and this has to come from currents. So currents means charges going back and forth, and then producing aurora actually on Jupiter. You can see kind of like these dots here belong to the moons that are magnetically connected to the moons. I mean, and this is aurora on Jupiter's atmosphere.
That is super interesting. Thanks a lot.
Um, could cavitons form on Jupiter?
That's a, you mean foreshore cavitons?
Yeah.
Yeah, that is a good question. They probably should, but the problem is I don't think that the foreshock of Jupiter is very well studied. And the reason for that is that since the magnetosphere is so massive, a spacecraft orbiting Jupiter, like Galileo or Juno, they were orbiting much inside of Jupiter's magnetosphere. So we only have data, I think, from like orbit insertion phases and things like this, or like the first orbits. So we have very few data points, actually, I think, of Jupiter's foreshock. The other thing that is complicating this is that the further you go out, the more kind of like not non-radial, how do you say, oblique, the interplanetary magnetic field becomes, because it kind of like spirals out into the solar system. So at Mercury, it's very radial. At Jupiter, it comes at like a 90-degree angle almost. I mean, on average. And that means that the foreshock region is also not located just upstream of the subsolar bow shock, but it's kind of like to the sides. So this also complicates measurements of the foreshock.
Okay, thank you.
Okay, we have two questions. De Luis Damián, lecture. I would like you to explain more about your participation in Hayabusa's mission and your experience with minor bodies.
Okay, so Hayabusa mission was before I came to the institute, so I can only say from what I heard. Okay, so I have no first-hand experience to say this. So Hayabusa mission was to asteroids, especially to Ryugu, and I think Hayabusa 2 was also a sample return mission, but it contained a German lander. So and the lander was Mascot 2. It's kind of like a box, like a shoe box, essentially. And from the spacecraft, the spacecraft just hovered over the asteroid, and it was just dropped onto the asteroid. And it has like a mechanical mechanism by which it could perform jumps to see to like go to other landing positions. A little bit of also different instrumentation and the magnetometer, and to study, for example, if the asteroid actually had a magnetic field, and it didn't have a magnetic field. Okay, so this was one of the conclusions from that mission. I don't know if there were many studies also working on induction, for example, but it was of course an asteroid in the solar wind. In respect to small bodies, much more came out, for example, of the magnetic field investigations with Rosetta near the comet 67P, Churyumov-Gerasimenko. And that comet also did not have an intrinsic magnetic field or crustal magnetic field. But since comets also have a lot of outgassing, this outgassing is then gradually ionized due to UV emissions from the sun. This coma is also interacting with the incoming solar wind and has a very rich kind of magnetospheric type or bubble type of interaction region also inside of the solar wind. And from these also multi-point measurements could be performed over a short period of time between the lander and the orbiter that were very interesting. Also because, for example, close to the comet or to the comet nucleus, like a diamagnetic cavity could be detected, like a field-free zone, so to say, from the outgassing, and studied like there are many different waves, high amplitude waves, and so on, came out of these studies.
Okay, bueno, quedó respondida la pregunta de Luis Damián. Otra de Alma Karen. The jets only have been found out in the Earth. I think you already said.
Mm-hmm. Yes. But the problem is that we are lacking good data from the other planets to do this. So I think this is the main point. It does not mean that it doesn't exist, because there should be universal processes. But so far, we really don't have the data to pinpoint that jets have been observed somewhere else. And interplanetary shocks, I think Heli Hirtala has performed a study to show that there existed interplanetary shocks.
Okay, de aquí del público, otra pregunta.
Thank you very much for a very interesting talk. It's a quick question. How is the data recovered from these missions?
Mm-hmm. So, well, for example, with JUICE and Bepi Colombo, there is a direct link with a deep space network. So so with like, I don't know, 35 or 70-meter dishes to communicate with the spacecraft. Then for missions like Mascot and Hayabusa, the connection is from the ground to the main spacecraft, so to Hayabusa, and then there is a inter-spacecraft link to the lander. And the same also applied, for example, for Rosetta. So the lander Philae was taking contact, or it was in contact with Rosetta, with the orbiter, and then Rosetta was collecting the data, and then every now and then actually aligning its high gain antenna with the Earth to have like a yeah, high in quotes, high data rate link to the Earth.
It's received in where?
It's received, well, this is all deep space network. So there's, I think, a couple of, there's like one in the US, one site, there's, or several. There's one, I think, in Madrid in Spain for ESA, and I think one also in Australia for Canberra, I think. So there are different sites to receive these.
Thank you very much.
Bueno, si ya no hay alguna otra pregunta, dar las gracias a los invitados del Seminario Extraordinario. Muchas gracias.
Thank you very much.